Party being start class. That's the term. So welcome back, folks. As I sent out over email, I think yesterday morning, I pushed back the deadline for homework 3 to next Tuesday. That way we make sure we have time to go over the remaining models as well as tackle any questions on how to do that in homework, and quiz 2 also to the following Thursday. So that is available in Canvas. I realized after class that I probably need to talk about, in order for you to do homework 3, I need to go over the ML versus REML thing more thoroughly, because I sort of brushed by that because it's not relevant a lot of the time, but I want to make sure that you're aware of it because that's where the world of software and modeling interfaces. These choices aren't available in every software package, and so I want to make sure you know what you're doing with respect to that. So where I would like to start actually is the end of lecture 3. This is slide 23. There we go. Streaming. So yes, picking up in lecture 3 at the end, slide 23 is where I wanted to start. Talk about ML versus REML and model comparisons. So big picture, in asking ourselves what needs to be in a model, there's 2 types of models that we're talking about. There's model for the means, there's model for the variance. When you're talking model for the means, that's fixed effects. That's effective predictors that explain variance. We don't need to do anything with respect to log likelihood to answer questions about fixed effects. Each fixed effect gets tested against a null hypothesis of 0. That's a univariate wall test. And a set of fixed effects, such as an omnibus main effective group or a set of predictors making the model better to test change in R-squared, that's a multivariate wall test done either as an F or a chi-square. So everything that we're talking about here is not about the effective predictors. It's about the model for the variance. That is, how many different parameters do we need to describe the pattern of variance and covariance across occasions from the same person? So that's why you haven't had to deal with log likelihood very much in models that we're focusing on the effects of predictors. It's only when we start talking about variances and covariances that this becomes relevant. So each model has its fits summarized by something called log likelihood. It's a single number that describes how tall, and I will talk about the equations that go into this in the next unit, but just briefly conceptually, it's how tall is the data given the best choice of model parameters that it can find. And each person has a likelihood function. Basically, you take each person's set of data, you plug into it the best guess of the parameters, and you come up with a likelihood value for that person. If you take the log of it, then you can add the values across people because people are supposed to be independent. And so that number then is the height of the model, where you want bigger is better. Now to make things complicated, the difference in these heights is distributed approximately as a chi-square only if it is multiplied by -2. So because you're eventually going to have to multiply the difference by -2, some software packages make it easier on you, and they give you the -2 version of log likelihood instead. So this is where what you put into the likelihood ratio test varies by software package based on what they're giving you. So if they give you something called -2 log likelihood, the metric of that is backwards. Because it's log likelihood times -2, smaller is better. So think of it as lack of height, shortness. Where log likelihood is height, tallness, this is shortness instead. In Stata's version of mixed and in M+, they give you the original log likelihood instead, where bigger is better. What does R give you in like Elmer or those ones? Do you know?
I want to say it's -2 likelihood.
It's -2 log likelihood. Does anyone else know? In R packages for mixed models? No? Okay. This differs even across different versions of SAS. Like if you use procgenmod versus proclogistic versus procglimics, some of those give log likelihood and some of those give -2 log likelihood. So you got to know which one you're starting with so that you know what to do with it. And log likelihood or -2 log likelihood comes in 2 flavors. There's the log likelihood under maximum likelihood, and there's the log likelihood under residual or restricted maximum likelihood. which is a different kind. So either way, whether it's ML, maximum likelihood, or REML, residual version, we have a likelihood ratio test to test differences in model fit. So this is where we are messing about with the model for the variance specifically. So is unstructured what we need, or can we get by with something simpler? Is compound symmetry good enough, or do we need to add something to make it more complicated to better map the data? When we're asking those kinds of questions, this is how we answer them. So a -2 log likelihood difference then is what we're after. So if the program gives you -2 log likelihood, you just take the straight up difference between models. And the order is important. It's the model that has fewer parameters minus the model that has more. Always. So in your homework, there are multiple choice questions where I ask which of these results in a valid model comparison. This is one of the rules that I'm looking for you to understand in looking at the choices. Some of the wrong answers break this rule. Fewer minus more is the only way that you're guaranteed to get a result that's positive. If you're given regular log likelihood, then you have to take the difference of fewer minus more times -2. Either way, you end up at the same number. Degrees of freedom for the comparison is the number of parameters that differ between models. So the number of things you've added or the number of things that you've taken away. If the models differ in things that you have added and taken away at the same time, they're not nested. It has to be one or the other for it to be nested. You have to be able to describe it as a subset. The difference in -2 log likelihood then is distributed approximately as a chi-square. And I say approximately because the statisticians in the world will yell at me if I don't add that. And there's an asterisk behind it that we'll talk about in the next unit as well. But for all intents and purposes, it's a chi-square with degrees of freedom equal to the difference in number of parameters. And you can get an exact p-value out of software or look it up in Excel using the chi-square distribution. Question? Sure.
So here, if I remember correctly, we have to ensure that the main structures are the same for the two models. Or are we just saying that one main structure, the main structure always can differ as well?
Depends.
Okay.
So this is the ML versus REML complication. So the question was, what about the mean structures? Don't they have to be the same? Sometimes is the answer. So we'll get to that in just 1 second. So one other thought here, AIC and BIC, for whatever reason, even programs that give you log likelihood instead of -2 log likelihood give you the same AIC and BIC that starts with -2 log likelihood, always. I don't know why this is. So AIC and BIC, as well as AICC and BICC and BIHC and whatever other permutations you get, smaller is better. There's no significance test though. So any kind of smaller is better. Now, where they differ is in the type of penalty that they imposed for model complexity. AIC is 2 times the number of parameters, whereas BIC is the natural log of the sample size times the number of parameters. So this seems straightforward, right? But it's not actually. So there are 2 things to keep in mind here. The log n, by the way, the sample size. We know how much that is, right? Which sample size? Level 2 sample size? Level 1 sample size? Programs disagree on what n is. So within a program, it will be internally consistent. It will always use the same version of n, but across programs, you can get a different BIC based on what they call n. What SAS does is n at the highest level of the model. So in this case, it's level 2. That changes in models with cross-random effects where n is 1. It's the number of unique combinations across the crossings. So this can vary between programs, but it should be the same within programs. So if you're running a series of models, you can look at the BIC across them. AIC and BIC will also be internally consistent within REML or within ML, but you can't mix across the 2. The other thing that's different is number of parameters. And so I have this down here because this is being drilled into you with practice for your homework. Number of parameters is all of them if your log likelihood came from maximum likelihood, meaning the number of model parameters in the means model, as she said, fixed effects, and the number of parameters in the variance model. In REML, number of parameters disregards the means model completely. It's only the variance model. Unless you're using stata, which counts both for REML. So this is where people can get different results across packages, even if they're ostensibly doing the same thing, is because of these nuances.
And logarithm is natural logarithm, right?
I'm sorry?
The log
Yes.
is element.
This is natural log. Yeah,
I didn't read the chapter before doing the homework and I messed up doing everything with 10 logarithm. Then I realized.
Yes, because if you type log in Excel, it's log 10.
Yeah.
If you type log in SAS, it's natural log. If you want natural log in Excel, it's ln. So yeah, you got to be careful with which log this is. But in stats, generally speaking, it's natural log for things because it works with exponents. So it's always that. So number of parameters differs across ML and REML. So in the very first section of your homework, when I give you a -2 log likelihood and I describe what the model is called, what I'm looking for you to be able to do is take that vocabulary and map it onto a reference for what must be in the means model and how many parameters it's going to take, what must be in the variance model, how many parameters it's going to take, and then look, is it ML or REML, and which of those parameters are going to count towards the AIC and the BIC. So it'll be easiest for you if you just set up a spreadsheet. That way you can easily calculate AIC and BIC for these various combinations. So the logical question then is, why does REML only count some of them? That doesn't make any sense. Why is there this difference? It goes into the kind of fit that each, I don't want to say algorithm, function, let's call it function, is trying to keep track of. So you probably have never heard of residual maximum likelihood before because it's only present in mixed models that have normal residuals. It's only a thing for that specific type of model. So mixed models meaning models that have fixed and random effects or just fixed effects. So REML is least squares, by the way. I could do the math for you, but I'm not good at proofs. Or you can read the chapter in the Ender's book, I think it's chapter 4 or 5, where he shows where this stuff comes from. REML is least squares. So if I run the exact same model in proc mixed that I run in a regression piece of software or in a ANOVA piece of software, I get the exact same result. Where they differ is incomplete data. REML allows for incomplete outcomes from the same person. Least squares cannot, because everything has to have some kind of sum of squares to make the thing go. So the formula by which variances are either estimated or calculated, depending on whether you have missing data, is n minus k on the bottom for the variance thing here, where k is the number of fixed effects. If you look down here, regular flavor maximum likelihood is missing the minus k. That's the difference. It boils down to what you may have been told sample versus population in estimates, where population you don't have to acknowledge the fact that you've estimated something to get the variance, whereas in sample you do. Because what do you have to know to be able to compute a variance? Well, the predicted y. At a minimum, that's predicted based on the mean. It's predicted based on other stuff in more complicated linear models that have regression or ANOVA types of things. So this n versus n minus k is the difference. If you have a big enough sample size, they converge onto the same number. Where this differs is in samples that have small numbers of level 2 units. So if I have like 10 people measured 4 times, this is going to make a big difference in how much variance I have across people in my random effects, intercepts, and slopes. So REML is the default in every mixed modeling package that I'm aware of. HLM mixed in SPSS, Stata, SAS, and I want to say even ML-Win. I'm not for sure about that one though, but REML is the default. You have to override it to get to ML. ML is what you learn about in every other class. ML is what runs confirmatory factor models, structural equation models, item response theory models, logistic regression, any kind of nonlinear regression. That's regular flavor ML. And that is missing the minus k. So the random effect variances end up being too small because of this difference in the denominator in small samples.
Can you talk more about the full information maximum? Like, is it always the same as ML in various contexts? Because it always confuse me when some of the literature in SEM or CFA, they claim that they use the full information maximum likelihood, but I'm so confused. What is the difference between the regular ML or are they the same?
Full information or regular ML? Okay.
In terms of the missing data. I
In
think
terms
they
of the missing
handle-
data.
I think they handle the missing data differently.
Yes.
Okay.
Great question. Okay, so this taps into more broadly in the world of statistics. Oftentimes, if you're like writing a grant proposal or you want to sound fancy, you need to throw an FI in front of this. Full information maximum likelihood. It's better, does everything, handles missing data. By the way, handle is a phrase that you want to avoid because it means you don't know what you're talking about. People who don't know what they're talking about say, just it handles it. How does it handle it? It does. I don't know, it's fine. Leave it alone. But I know that that is a common phrase, handling missing data or handling non-normality or handling dependency, right? That's what we're going to do. We're going to handle dependency in this class. But the term full information, what it means is that what goes into the likelihood function is the original data. Each person gets a value that summarizes their set of observations. And the formula that provides that value is essentially the multivariate normal distribution formula. You plug in the data given the parameters and out comes a number. And so the idea of full information is that each person's likelihood number, it's a shape. I can't draw it in multidimensional space, but it should have the same shape even if they have missing data. That's the assumption of missing at random. But we can add together each person's likelihoods. If my likelihood is based on 2 observations and yours is based on 3, no problem. Just stack them all up and I've got one value for the sample for the total log likelihood. Full information is also how REML works. But for reasons I will never understand, it's never called FREML, the way it's called FIML. But it should. So I'm gonna start it right now. I'm gonna start a trend for REML as a thing. Because REML is full information too. That's not how they differ. Now, what is limited information, or what happens when you have missing data? The phrase limited information means that the model is not estimated using the original data. It's estimated using a summary of the original data first. So if you have complete data, and you compute the covariance matrix for your complete data, you can do that as an option if you ask for a correlation matrix, right? You can spit out the covariance version. You also know how to do this as type equals UN in SAS, because the unstructured matrix is just the original data. If you have complete data and you spit out that covariance matrix, and you feed that covariance matrix as input into a mixed modeling package or a structural equation modeling package, you will get the exact same answers back as if you read in the raw data. Because when the model is normal, meaning normal residuals and normal factors or normal random effects, factors and random effects are the same thing, folks. So when I say a random intercept, you can think of yourself as a latent variable. You'll get the same thing if there's complete data. So this distinction of full information versus not doesn't matter if you have complete data and normal. Where it matters is if you have incomplete data, because if you summarize the data first and you have a covariance matrix and you feed that covariance matrix into a program, the program doesn't understand that the covariance matrix is missing some stuff in it, right? It doesn't understand that some of those might even be not possible because of the different combinations of pairwise missingness. So you can get different answers, and then you do have to worry about the inference that you're making. The people who didn't answer certain questions might be fundamentally different than the people who gave you complete data, and then what kind of population can you make inference to, and all that kind of stuff. Where this matters is when you're fitting models to non-normal outcomes. So in M+, for instance, if you do structural equation modeling for categorical responses, binary responses, Likert responses, that kind of thing, then you get different answers if you do full information versus limited information. And limited information assumes missing completely at random because you're starting with the summary and the summary doesn't know how it got there. Whereas full information starts with the original data. So does that help? So these are both full. They use the original data. That's not why they differ. They differ in this n versus n minus k thing. And that, for that reason, REML is preferred in smaller samples. If you have a big enough sample, it doesn't really matter. Now, because of the difference in the number of parameters that they keep track of, that's where you get into the rules about what kind of models you can compare in each. So here's a table that puts it all together. So if you're using regular flavor maximum likelihood, that's n on the bottom, doesn't take into account that you had to estimate fixed effects to get to the predicted outcomes. Therefore, in small samples, the random effect variances are going to be too small. However, ML is convenient because it indexes the fit of the entire model at the same time. That's why when I say number of parameters for AIC and BIC, if you're in ML, it's all of them, because it's tracking the fit of everything. So you can compare any kind of nested model that you want to if you're in ML. It can differ in fixed effects, random effects, or both. So on your homework, in which of these comparisons will result in a valid test statistic, I'm asking you to recognize this as well. The order has to be right and the type of model being compared. If it's an ML, it can be on either side. Where it matters, and your question a couple minutes ago then was about the mean side being the same. That's a REML thing. REML operates on the residuals of the model. It doesn't care how the means model got those residuals for you. It operates on the residuals itself. It doesn't keep track of what fixed effects were estimated. So in comparing models estimated in REML, you have to keep the means part, the fixed effects, the same, or it's invalid. Now that's actually not a problem. The way that I tend to operate in model comparisons, if I add something fixed, I stare at the p-value that shows up on my output, the wald test, or I ask for a contrast statement to compare multiple fixed effects. I don't need a model comparison. I need model comparisons when I mess with the variance model. And if I'm messing with the variance model, I want to isolate that by keeping the fixed part, the means model, the same. So when we get to models with fixed and random effects, we'll add the fixed part, check the p-value, then add the random part, do a likelihood ratio test, and we're fine with these rules. So in practice, the only way to screw this up is to use REML, change both sides of the model at the same time, and do a likelihood ratio test. That's the one wrong thing you can do. The other thing, so here's a table that gives you a chart here. If the models are nested and you're interested in comparing a fixed effect, you could stare at the p-value that comes from the output. That's a univariate wald test. Or you can do a -2 log likelihood difference in ML only. If the models are non-nested, then it has to be an ML so that you can look at AIC and BIC. If you're messing about with the variance model, so what kind of structure you have is what we're talking about now, or what kind of random effects you need, you are not allowed to stare at the p-values that come on the output. That's the thing that our email exchange was about. We'll look at that today. If you do, there are like 10 people in the world who know the difference and will yell at you. And just in case one of those 10 people is reviewer 3, I want you to know this. No wald test for variance model things. -2 log likelihood is the way to go. And that can be in REML or ML. If you change both at the same time, I don't generally advise that, but if you want to do that, it has to be ML for it to work. And there's one more rule at the top here. This one holds regardless. The exact same set of observations has to be used in both models for any kind of comparison to be valid. So I have a, at the end of my advanced multi-level class, I used to do You Play the Consultant as my final exam. It wasn't an exam, it was take home. But I would ask people, like, pretend like, you're the stats consultant and people are coming to you for advice. And one of my favorite questions, because it always trips them up, is, I added a predictor to the model. The p-value for the predictor, for the fixed effect, said it was non-significant, but my log likelihood went down by like 200. How can that be? And people usually start talking about ML versus REML, and if you know some, no, that's not it. It's a much simpler explanation. Log likelihood is height of the data. If you have less data, it's less tall. So how your log likelihood can go down a whole bunch, even if you add something non-significant, is because you dropped cases that were missing that predictor. And that resulted in a completely different set of heights that would be relevant to compare. So you cannot do any kind of model comparison using -2 log likelihood, AIC or BAC, unless it's on the exact same sample across the models.
So can I rephrase it?
Please.
So what you mean is that if we add fixed effect
Mhm.
to the model, but that decreased the sample size because of missing, in that case, we cannot do model comparison.
Correct.
Okay.
Now, what you can do is stare at the p-value for that fixed effect and make a decision, but you have to acknowledge that decision is based on a subset of your original sample. Because here's the dirty secret. ML does not handle missing predictors. It kicks cases with missing predictors out of the model the same as anything else. So let me remind you of this. We'll talk about this when we get to predictors, but we talked about this at the very, very beginning of class when I gave you a sales pitch for why you should be here. Let me pull up this picture. This one. What happens to missing data? When you're using least squares, you have to be able to compute sums of squares across observations that are comparable. So all of the data points have to be there for you to be able to do any kind of hand calculation thing. That's least squares. In MLM, when using maximum likelihood, REML or ML, any kind of likelihood, and the same in Bayes, the same rule is true. It has to be complete. In Bayes, you have to do extra stuff if it's incomplete, and then that's a whole separate class. That's Friday's class, not today. But in regular flavor ML, the rule is the same. The difference is in what is a case. All cases have to be complete to go into the likelihood function. Anything that is incomplete gets dropped. So the good news is that for this person here who has 3 out of 4 outcomes, I get to use 3 out of their 4 outcomes. Their R matrix would be a 3 by 3, whereas the first person's would be a 4 by 4. But if this person were missing any time varying predictors, those rows are gone too. Missing predictors are not handled the same way as outcomes because they're not part of the likelihood. To invoke them as part of the likelihood, you have to tell the program essentially that they're another outcome rather than as a predictor. And then they have distributional assumptions, and then you can have missingness. So what to do with missing predictors in multi-level or longitudinal models is a very tricky thing. And there are multiple imputation procedures, but they're not as straightforward as when you have single level data because of the random effects that you have to be able to anticipate in the imputation model. So yes, bottom line, because of this missingness, your sample can change across models. If you want to use -2 log likelihood, it has to be the same sample. Okay, does that make sense? Okay. All right, so I think, yes, so here's yet another way of trying to summarize this. If the models are nested or non-nested is your first thing to recognize. Do the models to be compared differ in their fixed effects on the mean side, their random effects or structures on the variance side, or both? If it's fixed or both, the comparison has to be in ML. And if you're using REML, you have to keep the fixed effects the same. So that should hopefully help you get through the logic of a lot of the questions on the homework. It's just giving you practice understanding these rules. So any questions on this topic, ML versus REML versus any of this? We're going to live in REML this semester. We're going to live in REML, and we're going to test fixed effects using Wald tests, and we're going to test variance model things using likelihood ratio tests. That's it. Then you won't screw it up. Mm-hmm.
Summarize that. Why do you prefer REML over regular and quantitative?
We always prefer REML over ML. Always. But it matters to the extent that n is small. So if I have 10 people, I will get a very different estimate for my random variances, intercepts, and slopes if I use ML versus REML. In ML, it's too small. So that trickles down then because the standard errors of the fixed effects are based on the size of those variances, and the standard errors trickle down and are too small. And what happens if your standard errors are too small to your p-values? Too good. Yeah. So you can end up with type 1 error rates that are too high if you use ML with small samples. Now that being said, what about structural equation models or IRT models or CFA models? Would you ever try to run one of those on 10 people? Nope. This is partly the reason why. Asymptotics. So REML is always better. It stops mattering after, and this is where there's a ratio, right? So there's some point at which you hit asymptote. The literature says 50 level 2 units-ish, but it also depends on how complicated your model is. So I would actually say maybe 100 would be like where I would feel comfortable just going with ML and calling it good for the number of level 2 units. It's the highest level units that matters, not the lower. So let's say that you are studying educational data and you have access to every single student in Iowa. That's a lot of students, right? But if that comes from only like 10 districts, students and classes and teachers and schools and districts, and you only have 10 districts and you want to model district variation, you better use REML. Even though you have like 8 million children, you have 10 districts. It's the highest level of the hierarchy that dictates this N. And there are, to my knowledge, no packages that do structural equation modeling that also do REML. It's not in M+, for instance. It's not in AMOS. It's not in EQS. I'm pretty sure it's not in Levon either. So.
I have a question.
Yeah.
So the highest level, that means if we only have one class students exempt scores, then the highest level is just individual.
Mm-hmm.
So that in that case, the N is good enough.
Yes. So this would matter, like if you ran a regression on 5 people, then this problem shows up. If you ran it with REML, least squares, you'd get one different answer for your residual variance than if you ran it with ML. Yep. By the way, the response that I give, I've actually published papers with small samples. Do you know what the smallest is that I have in print? Wasn't my data set. I was just sort of like the 7th author because I helped them a little bit. 9 people. They had 21 occasions. And all they were interested in was time varying stuff. And I've had reviewers, I had just had another paper actually just published in PLOS 1. It was a project of a student in my longitudinal class that we finally got published like 10 years after she was in the class. So it was like a long time coming. It was 8 people. And one of the criticisms from the reviewers was like, 8 people? You're doing multi-level modeling on 8 people? I only had a random intercept in my model. What do you know a random intercept only model as, in general linear modeling terms? Give you a hint, skinny jeans. Compound symmetry, that's ANOVA. So if you'd be okay with me doing a repeated measures ANOVA on 8 people, you better be okay with me using REML to do the exact same thing in a mixed modeling package. So REML is least squares. And if I ran the world, you would never have bothered to learn sums of squares, F-tests, estimated mean squares, or any of that crap, because that doesn't scale. I'd start with REML and we go from there. But I don't run the world, so. All right, other questions? Okay, so that I wanted to make sure we had clear. And then we can talk about PANTS, or alternative covariance structures. That's where we are. All right. Ismail, you don't look happy. Yeah. Did it make you sad when I said I don't like sums of squares?
Yeah, I love it.
You love them? Okay. I know it's nice and like reassuring when you can compute it and like make it work. But the problem is that once you get into the world of real data, where things aren't always like perfect, right? Then it's like ugh, you can't sums of squares your way around missing data or non-normal outcomes or clustered samples or anything like that. That's where it breaks down, right? And that's the world I live in. So the world of messy data, which to me is a redundant phrase. I've never met a clean data set that came from real people. Maybe I'm hanging out with the wrong crowd, but I pretty much think that, you know, if you collect data from people, it's inherently messy. All right, so this topic that we're in right now, this covariance structure stuff, it is one of the things that it's hard to teach because there's little that I can do to be enthusiastic about it, and I don't want it to become just like a rote memorization of like, oh, here's my AR1 and it has this, and compound symmetry has this. I want to make sure that you're following the bigger picture of why am I even talking about this, right? Because it bores the hell out of me, quite frankly. Chapter 4 was so boring to write. I got to tell you, I hated it. But I felt compelled to put it in there because it's important to a lot of different types of fluctuation data that are becoming increasingly common when you can buzz people on their phones and have them fill out surveys multiple times a day. So I just wanted to back up here and try to organize like what we're doing here. So first question, like what is this unit about? What is chapter 4 about in the first place? And I would say, if I were talking in terms of statistics, I would say something like finding an appropriate model that, let's say approximating variance, covariance matrix over time or something like that. Like that's what we're trying to do. How are we going to do it? Well, we have R matrix structures or G and R matrix structures. Those are our choices that we can have. We're going over those. Why are we going to do it? Why does it matter? P-values for the fixed effects. Everything works backwards. Where does the p-value come from the fixed effect? Well, part of it is a reflection of the standard error of the thing you're trying to estimate. Where does standard error come from? The numerator is variance. So you have to be able to describe what is the variance like in my model so that you can trust the standard errors that come with it. And so I try to come up with real-world analogies that would map onto this sort of process because we're not doing anything that would pertain to hypothesis testing of interest directly. Like I said last time, no one ever in their life has woke up in the morning thinking, I wonder if my data are an AR1 or a turbulence. If you wrote a grant proposal to NIH with that as your specific aim, it would get rejected just for asking that question. No one cares. And indeed, if you have to go through this process with real data, that is going to be like a tiny paragraph in your results that says, we checked all this stuff and made sure that the variance model was good. Okay, let's move on. No one cares. So given that no one cares, what is a way to describe why this is important in the first place? What are we trying to do? And the analogy I want to use for this is reliant on a sage advice of a woman named Susie Orman. Have you heard of this person? Nope. Okay, I'm dating myself. She is a financial advisor. She went on the Oprah Winfrey Show several times, and everyone loved her, and she has her own show on CNBC. Went off the air a couple years ago, and she's doing other things. But people would call in, and she would answer their questions about money in a very straightforward way. So she became sort of like the speaker to the people. And I used to watch the show while I painted my nails. I was going with a green glitter this week. And so I could feel better about myself. Because invariably, people would call in and be like, I have $1 million in credit card debt, and I have $1 million in student loans, and I'd like a new car, and I'm wondering if you can tell me if I can afford it. And I'd be like, well, relative to that, I am winning. You know, I may have no money, but I don't have that much debt, so I feel good about myself. So she would try to counsel these people, and some of them realized that they were in trouble. A lot of times debt was the problem. The very first thing that they had to do, though, was not figure out how they're going to pay off their debt. It was figure out what their debt is. Because these folks had been afraid for so long, the bills come in the mail, they don't even open them. No idea how bad it actually is. So step one before we're trying to do anything is figure out how much debt you have. Because then once you realize that I owe company X this much money and company Y that much money, but company X is charging a higher interest rate than company Y, so I need to pay company X off first. Making that kind of a plan then gives you the steps to action. So if I think of this in terms of data, what we're going through is just trying to figure out how much variance and covariance we have. We're not trying to pay it down. We're not trying to reduce it. We're not trying to explain it with fixed effects. We're just trying to figure out how much we have. Because when you have multivariate data, it's not as easy to do as if you have only one outcome. So how much variance do we have? How much of it is across people? How much of it is across time? Does the variability increase across time or decrease? And what kind of covariance do we have? We're just trying to figure out the map of what's there before we can then tackle it. Before paying it down. There we go. How? Well, pants analogy. I'm going with different choices. Anal, O-G. That looks better. These are all the different ways that we can try to approximate the pattern. How do we make a model that mimics what the pattern is? That's what we're trying to do. And so we've been through one set of choices, the R matrix choices. We'll review those in just a second, and then we have the second set to do today. And then the Y, to make sure that the, painting, that's the analogy I want to use it. To make sure that the fixed effects are tested as accurately as possible. And the analogy I have for this is painting. Do any of you own homes yet? Good. That is the correct answer when you are not yet where you're going to be. But as a grad student, I used to watch a lot of HGTV. It's like the decorating shows where they go and paint everything and make it look nice, right? Because I was in like a beige apartment with beige carpet and white walls, and it was so boring, and I just wanted to, you know, paint my room yellow or something. Turns out painting, a lot less fun than they make it look on the shows. Because it's not just about walking into Home Depot and picking up the perfect shade of yellow and taking it home, right? No, no. First, you have to remove all of the light fixtures, all of the electrical outlet things. You have to sand the wall. You have to remove all the nails. You have to fill all the holes. Then you have to apply tape over all of the edges so that you don't slop your yellow paint everywhere onto the woodwork. That process takes a really long time, and it's boring and not any kind of fun. But you have to do it if you want your paint to look good at the end of the day. And so this process, looking at our AR1s and Topolitzes and looking for differences in fit is boring. But we have to do it if we want to have fixed effects that look nice and yellow and trustable at the end of the day. The same is true in manicures. But I'd be happy to go over my manicure techniques if anyone cares. But it's actually very similar to painting, as it were. The prep work is everything, not just the color. So, you got that, James?
Got it.
Okay. There's going to be a quiz over this later, so I'm going to make sure you're paying attention. Right?
Is there any situation that people don't care about the fixed effects and they're more concerned on the random, like subject specific stuff?
I have a hard time coming up with an example in this context, but I can give you an example in a different context. If you're making up a new scale and you want to know whether or not the items that you've created are unidimensional such that you can think of them as measuring one construct, that's this. The factor analytic model is another kind of pattern. It's characterized by loadings and residual variances and factor variances as its parameters. In fact, in proc mixed, there is a repeated option type equals FA, factor analysis. In that case, what you're trying to do is see if the pattern of covariance across your items is consistent with the idea that they're measuring one thing, albeit unequally well. There's no fixed effects in that story whatsoever. You can have the means of the items in the model, but you don't usually care about them. I have a hard time in this context thinking of an example where the question is not eventually about the fixed effects, but sometimes people want to know about variability across persons, whether or not there is evidence that people change differently in the first place. That might be controversial. But then usually the second half of it is if there's individual differences in change, how do I explain it? Is it because drug A works better than drug B, or because neuroticism leads to greater cognitive decline, or something about the fixed effects? So they always seem like they show up in there otherwise. I don't know. Do any of you have examples you can think of where you might care only about this variance part? No, I don't have any. But so yes, we're not explaining variance yet. That's coming. This is the prep work that we have to do so that the model that we fit later is trustable. Okay, you with me?
Yeah.
Yeah, you're with me. You're nodding. You with me? Yeah, you're nodding too? You're not with me? He's like, we're with me? Okay. So, big picture. Trying to find a pattern so that the model represents the pattern of variance and covariance as accurately but parsimoniously as possible. So then we trust it when we go and add stuff later. Add fixed effects later. So the patterns that we looked at before are matrix only patterns. So the endpoints we talked about, compound symmetry, random intercept only plus a residual is what makes the variance over time. Random intercept is what makes the covariance over time. 2 parameters, regardless of how many occasions you have. Other side, most complicated thing you could ever have, unstructured. Everything gets to be what it wants. Only possible in balanced data. May not be possible if you don't have a lot of people. We're trying to find something that maps as closely onto unstructured, but uses fewer parameters. So we looked at, let me get out the example from last time. Real data. Outcome is psoriasis severity fluctuating across a 7-week period. So intra-class correlation of 0.84. Remember what that means? Intra-class correlation of 0.84 in this example. What's that mean? Yes, it's 84% between due to mean differences, due to cross-sectional differences between people, yes. Here's the right answer for this example data set. The variances were mostly the same over time, at least for a little while. A few of them are a little bit different for reasons that we don't know. If we look at the covariances over time, Rather, the correlations makes it easier to tell the magnitude. The average correlation over time is 0.84, but we see some variation around that. Occasions that are closer together tend to be more related. So we're looking for a model that mimics this pattern. We did AR1. In AR1, our matrix has only two parameters, a total variance and an AR correlation. The correlation is becomes the model predicted correlation between occasions 1 unit in time apart. That AR correlation squared is 2 units in time apart, cubed is 3 units in time apart, and so on. That didn't fit very well because it predicts a correlation that decays way too quickly over time. Tapered pants was the analog there. We looked at toplets, which is banded, also requires equal interval data in this setup, but each band gets a separate estimate. So this time we have the same variance over time, so we can look at the correlation table down here. Occasions 1 unit apart have one value, 2 unit apart have the separate value, 3 units has a separate value, and so on. So this 7 after it, that refers to the number of parameters. That's the number of occasions. Not all software allows you to mess with that. SPSS does not, and I believe Stata does not, if I remember correctly. SAS does. That one fit almost not worse than unstructured. And so we tried to add different variances to it, change it to a heterogeneous variance model, but that did not fit better. And it now fits officially worse than unstructured, and that's where we left off. So these models, let's see, this is, yeah, I want this one. These models that we've looked at, compound symmetry and its heterogeneous counterpart, AR1 toplets, they operate by trying to put everything in one matrix. The total variance and covariance across occasions and people all in one matrix, and they try to find a pattern for that. An alternative way of thinking about it is to start from the perspective of the sampling design and go from there. So we have between people, we have within people. What's the pattern that we need for each separately? And then when we combine them, we get the whole variance and covariance back. It turns out to be easier to pattern each level separately than to try to pattern the whole thing at the same time. So the models that we're going to talk about then, this other family of models, picking up on slide 16 of lecture 4. These start from compound symmetry as its most restrictive version, but they expand in a different way than the previous models. They explicitly separate between person variance and covariance from within person variance and covariance. So now we have some new letters. If we're going to go this route, R is no longer the total, but R is going to refer to level 1 specifically. It's the repeated statement. We're going to add G to talk about level 2, which is a new statement that's going to be called random. This is the notation that SAS uses. I've seen G and R used in other places too. I think it's reasonably common. And when you put them back together again to form the total, that new total is called V. This group isn't afraid of matrices, right? No, you're not? I am. But for those of you who are thinking, how can you put G and R back together again? They're not even going to be the same size. You're right. You have to pre and post multiply G by another matrix which holds the values of predictors that have random effects so that it's the right size. So it looks like this then. So compound symmetry is the total form that you get under this approach if you take a random intercept variance and put it in G, G is level 2, so it's not really a matrix, it's just a scalar. But this G matrix is going to have other stuff in it next week, so we got to learn the words. And then what's left has this VC pattern for the residuals. VC means variance components. It's the same assumption that we have in regression of independence and constant variance. So what this is saying is that after we take out the reason for the covariance according to this model, which is random intercept variance, what's left, the E's, has constant variance across time with no covariance whatsoever. Said differently, we have handled the dependency in the longitudinal data, the fact that the occasions from the same person are more correlated, by taking that dependency and saying it's U0. U0 variance is my dependency. Once I handle it, once I move it out of the way, stick it over here in G, what's left is independent with constant variance. That's the jumping off point, because this is an empirical question. Whether or not this R matrix, this simple version, is enough, we got to add to it and see if it's good enough. And if you aren't a matrix person, you can visualize how these two things get put back together again as just thinking that the random intercept variance gets stuck everywhere in this matrix and then it looks like that. If you are a matrix person and are not satisfied with that answer, I don't blame you. Here's what it actually looks like. In order to make a total matrix that fits each person's data, we have to know how many occasions each person has. Right now, the only kind of random effect that we have is an intercept. If you represent an intercept as a variable, it's a column of ones, right? So if I have 4 occasions, so each person is going to get their own little variance-covariance matrix here. If everybody has 4 occasions, then everybody's matrix looks the same. But if I have 4 occasions, then I have 4 rows of data. That's my Z matrix here. Z transpose, turn it on its side. If you work through the multiplication of this, it becomes a 4 by 4. We can then directly add, in the matrix algebra sense, the expected variance at each occasion due to level 1 residual, and you end up back at compound symmetry. Now this formula right here, Z times G times Z transpose plus R, let me go back. Where's that formula? Right here. Here it is together. Does that look familiar to anybody? The pattern of it, but maybe with some different letters. It's a quadratic form that allows this to be squared, yes. Does this look like another kind of model that you might have had in another class, maybe?
Principal components analysis.
Not principal components, but yes. This is a confirmatory factor analysis with different letters. Right? So G, it's your factor variances and covariances. Same thing as random effect variances and covariances. Z, that's your lambda loading matrix. R, I'm going to go with psi, errors. Yeah. Error matrix, we'll call it that one. Yeah. It's probably squiggle 1 in the notation. Makes me really mad when I read SEM textbooks and squiggle 2 is used for G and squiggle 1 is used for R. Because I'm like, really? Do you know what I mean? That's my name for the letters. I'm never going to learn the real ones. It's squiggle 1 and squiggle 2. But anyway, yeah. This is the same thing. So now that we have this nifty trick where we can separate out the variances and covariances that are supposed to be at each level, let me show you what it would look like to get an unstructured matrix so that we can figure out exactly what this E should look like according to the data. So the idea here is that, okay, we know from the get-go, from the empty model that just has this structure, that 84% of the variability is between. Let's just set that aside and focus on what's left. The analogy for this is taking your pants to a tailor. Pick out pants that fit the worst fitting part of you. Get that part right, and then let the tailor fix everything else. Much easier than trying to buy pants off the rack. So here's what it looks like if you try to fit the same unstructured model this way, where we take out the random intercept variance and set it aside in level 2G. Then we can fit an unstructured R matrix with one small catch. Unstructured means all variances and covariances are estimated separately. Everything gets to be what it wants. But we can't do that here. We can't have everything be what it wants and have one more thing. Under-identified. So we have to shut off one of the parameters of the R matrix to make this thing identified. And the parameterization that I'm showing you is to take the covariance at the highest time lag distance and force it to be 0. Now that might sound crazy. What, you're saying that the first occasion and the last occasion aren't related? That's not what I'm saying. I'm saying they're not related anymore after taking out the random intercept. Because when you put it back together again, V is the total. This is sigma, by the way, or S for the sample version. No, this would be sigma because this is the original data. This is the H1 model, folks. If you look at the structure here, random intercept variance shows up everywhere in this matrix, and it is the covariance between the furthest occasions apart. So if you fit this, then you can see how complicated this R matrix needs to be to approximate the data after controlling for the between-person random intercept variance at level 2. And it's going to be easier than if you had that thing stuck in here contributing all this extra variance and covariance. So let me show you then, in our example, wow, time flies in here. Goodness. I swear we were going to get done today, and then I just talked too damn much, apparently. Okay, so let me show you what this looks like here. I'm going to split my screen so that the top of the screen is the unstructured model that we looked at earlier. So what we did before, R only structure, repeated, type equals UN. Okay, everything in one matrix, that's the data. That is our sweatpants that always are going to fit. You find it, here it is. There's my variance and covariance matrix, that's R. On the bottom then, this is an alternative way to get the exact same thing that is going to be more convenient for us to then find more simpler models for the residual part. New statement, random intercept. The random line controls what goes in G. The random line is your level 2 model for the variance. The repeated line then must become the level 1 part. The repeated line controls the R matrix that is left over after moving all the level 2 variance and covariance out into G. So random intercept repeated type equals UN with a 6. The 6 means shut the last off diagonal off, which we have to do in order to have a random intercept also. So up above here is the R matrix from everything in one matrix. Down below is what we get in this partitioning approach where we divide it into G and R. Okay. Here's what R looks like after we take out the random intercept variance. So you'll note the last covariance is gone because we are assuming that the only reason it would have been there is random intercept variance and nothing else. That's for model identification. And here, here we go. This is the E variance at time 1. This is the E variance at time 2. The within part of the variance over time specifically. Now we can see whether or not that needs to be homogeneous or heterogeneous. Likewise, the R core matrix gives us the correlation among the E's specifically. The level 1 within person correlation. So if we look at how strong that is, the correlation between occasions that are 1 unit in time apart, it's hovering right around 0.5. 0.5 to 0.6 if you look at this first off diagonal. But then what happens after that? It drops off pretty quickly. There's a few instances in which it's a little bit higher, but it goes down. So if we take this level 1 R matrix and we add to it the random intercept variance in G to put it all back together again, because it's all one model at the end of the day, that's where we get V. The put back together again across levels. And lo and behold, it's the same thing as we had before when we didn't do this partitioning. It's the same model. It's like if you're trying to shuffle a giant deck of cards. It's really hard to hold them all in your hand at the same time. An easy solution, take some of them, put them over here, shuffle this deck, shuffle that deck, and then put them back together. That's what we're doing. We're cutting the deck in pieces so that we can shuffle each part, so we can figure out what the pattern is for each part. So this R matrix right here, that is a great candidate for an AR1 residual correlation. A relatively medium correlation at adjacent occasions that dies off pretty quick. So that's what the rest of this handout is looking at then, is how do I pattern this matrix that's what's left. So I'm leaving the top here as my answer key. Here's the next one, random intercept plus AR1 residual. Here's the predicted R matrix from the AR1 residual. Constant variance and correlation that decays over time, where the autoregressive correlation for the residuals is 0.5. When you put that R matrix back together with G, you get this V right here. Pretty damn close. So of the longitudinal structures for fluctuation types of data, this one's my favorite. I like this one because it tends to work. There's also a version of it that you can specify for unbalanced data. The other options that you can consider is a reduced form Topolitz. So Top 6, by the way, because we have to shut off the highest lag covariance for identification. And we can reduce this down step by step to see if each of these additional bands is still needed, which is what I did in the rest of this example. So I fit subsequent models then removing these latter bands of residual correlation and came up with it looking like we need a residual correlation for 3 lags out, but not after that. And then tested whether or not it needed to be heterogeneous in terms of its residual variance, and ended up deciding that it did, yes. And that was the end of the story. So the place that I ended up with, the final model had random intercept variance between persons. Within persons, each week had a different residual variance. And there was a correlation allowed between weeks 1 week apart, 2 weeks apart, and 3 weeks apart. And that was the structure that most closely approximated unstructured using the fewest amount of parameters. And so then the spreadsheet that went with this example, I've listed out all of the fit statistics and all of the relevant comparisons that one could make for this. So even though this handout took, I don't know how many, 13 pages, it would be like 3 sentences in your write-up because no one cares. But the purpose of this is now that I have a reasonably well-fitting model, now I can add my fixed effects of variables that change over time and have reasonable confidence that they're going to be tested as accurately as possible. We never know if we're right, but we can reject models that are more wrong and at least try to do the best we can. There. Apologize for going 2 minutes over. Questions before we adjourn?
I got one.
Sure.
So in SEM, we look at the local fit
Mm-hmm.
to identify whether there's like missing paths or like extra paths or something like that.
Mm-hmm.
So in here, longitudinal, do we have the similar like strategy or?
Yes, but you have to compute it yourself if you're using this piece of software. If you run this same model in M+ and ask for residual output, then you can get local fit information, but you'd have to set it up as a wide data format type of thing. I actually will talk about that later. There's no easy way within mixed type of software to add just like certain covariances, the way that you can just say like that one and that one get an extra covariance in SEM, but that's a software problem and not a model problem. Like in theory, if your structure fit great except that there was an extra strong correlation between weeks 6 and 7 and you don't know why and you just want to put it in, you can. Mixed won't let you, but that's a SAS problem or a mixed problem, not a model problem. Yes, great question. And so this, the final model comparison here, where we're figuring out that the chosen model fits non-significantly worse. This one, I think, is it? This one? No, it's right here. No, anyone. I lost it. That one. That one, that's it. The fact that my structure fits non-significantly worse than unstructured, that it would be your chi-square test in SEM. That's the analogy. The difference between your chosen model and unstructured, the best one. You want it to be non-significant. You want it to fit, right? SEM p-values you want backwards. You want the model to be non-significantly different. So that would be saying that your, where did it go? This V predicted matrix is not significantly different than the one created from the data. That's what you're going for. And it uses fewer parameters to get there. Okay. So we get to start lecture 5 next week then. But the idea of lecture 5, you can pack up while I'm talking. It's cool. I'm going off all the time. We're going to put some more stuff over here. So we're messing about really with the error part for all intents and purposes right now in fluctuation data and change data. We got to add some more stuff over here because there's going to be more than one kind of between person difference, an intercept as well as time slope. So we got to add some stuff over here and then see what we need to do over here. Okay? Okay. All right, let me know if you have homework questions. Office hours start now. So.